To start with the simulation, just click on the new button and click on the blank simulation. So we need to add the components. The first component that we are adding is Ethylene Glycol, C4H10O3, we call it DEG. Second is water. Third component is ethylene glycol, C2H6O2, we call this one MEG. Then we have triethylene glycol, which is C6H14O4, we call it TEG. And then we have tetraethylene glycol, that is C8H18O5, and the name is we can call it O4EG. And the last one is ethylene oxide, which is our reactant for O-2, and that is we call it EO. So after providing the components, we need to click on the method that we are going to use, and in this particular case we are using a CPA. However, to use CPA, we need to make sure that we are using the binary coefficients. We must have the binary coefficient values in their respective binary interaction parameters. For example, in this case we have two interaction parameters, that is CPA Kij-1 and then we have CPA Vij-1. So we need to make sure that we have the information for these two binary interaction parameters here. So the interaction that we are looking for is all the ethylene glycol with water. So the component one is the ethylene glycol, then we have ethylene glycol, then we have triethylene glycol, then we have tetraethylene, and then we have ethylene oxide. And the component J is water, because we are checking the interaction between all these glycols with water. Right, after providing this information, we need to key in the information manually. This one is 2 or 40319. Then we have connected 0.16 55556. I wrote down these values on the paper, so from where I can get from where I can read this information and create. It will be more easier if you have these values on your desktop. You can just copy paste straight away. These are optimized values for on experimental data. So then we can start providing the Bij, which is 0.0492591. Level 628. The last one is 0.97. Similarly, for the second binary interaction parameter, we also have the values between diethylene glycol and triethylene glycol with water, and the values that we have is not 19305. Right, after providing these values, we need to click on the run button and see if they give us any error. They give us some warning, which is okay, but they don't give us any error, so that's fine. So after providing this, we can click on the simulation window, where we can start adding the streams and the unit operations. Okay, so the first thing I need to do is add a mixer and call it V1 and add inlet stream, and the inlet stream name is AO-water. Right, and this mixer also has an outlet, so I can name it 1, but I can hide those IDs anyway, so just use the random names. After this, I will provide the inlet information for our need. So the information for material stream, the feed stream, which is entering at 25 degrees Celsius with 35 bar pressure, with a mass flow of 55,000, and same for ethylene oxide is entering. We'll make sure that the error tolerance will be as minimum as possible. Right, and then we can start to run, and then you can see if we face any warnings or any error. So far there are no warnings and no errors, so we continue with the simulation. So let me hide the IDs. The next thing is that we need to preheat this feed stream. So to preheat, we need to use a heater block, and we can call this one preheat. We need to attach the feed stream to the preheater, and then we can call with the preheat stream, or you can say preheat stream, and then I will hide this ID. If you so now we need to provide the information for the heater, which is the heater temperature is 170 degrees Celsius with 35 bar pressure. Again, the flash options, we need to make sure the tolerance will be as low as possible. Then we click on the run, and there are no errors. After this preheating, we need to use a reactor. We use our plug reactor, and the reactor we can call it EGRCTR. And we need to change the icon of the reactor. Yes, and that's better. And then we need to attach the preheat stream to the reactor, and the outlet of the reactor we can provide as R-out. Right, so in order for the reactor to run, we need to use we need to have our actions. So we can click on the actions tab, click on the new, we need to click on the journal selection, and then we can click on OK. For the reactions, we have 4 different types of reactions that is basically happening. These reactions are kinetic based reactions. So the first one, based on the power law, the first reaction is called MEG, ethylene glycol. That is the water is reacting with ethylene oxide to produce ethylene glycol. We'll provide the coefficients, and then we can start with a new reaction, and that one is called DEG, which is diethylene glycol, and the components reacting are ethylene glycol that we produced previously is reacting with ethylene oxide to produce diethylene glycol. Again, we need to provide the coefficients. And then we can have the third reaction, which is the diethylene glycol will further react to produce triethylene glycol. So diethylene glycol is reacting with ethylene oxide to produce triethylene glycol. We provide the coefficients, and then we need to add the final reaction, that is tetraethylene glycol, that is produced by reacting ethylene glycol with ethylene oxide, and we will get the final reactions. So all we have is these four reactions, and we need to provide the kinetic parameters for each of these reactions. So the first one, and all of these have the same kinetic parameters. The constant, which is 0004, the division energy is 0008, and the temperature is 176.85. The same, and then we can have the experiment information. We can provide the experiment information, and the same information we can provide for the rest of the other reactions. Right. And the temperature is 176.85 with the experiments. And similarly, we can do this for the third reaction. So 6.85, and the experiments. And finally, for the fourth reaction, we have the same information as it is that one is 176.85, and the experiments are in 1. So as you can see, the color is turned blue. It means like everything it requires we need to provide. Now, the final thing before we can close the reaction tab is to find out the activity of ethylene glycol. So this one is EG, and the value is 2. And this one is with activity with other components. Okay. And if you click on the kinetic summary, you can see all the summary of the kinetic parameters that we provided. Then we can have we can close the selection tab. We can go to the reactor itself, and we can provide the information in the reactor. The reactor is adiabatic type of reactor. The configuration of the reactor is 193 meter length, the diameter is 0.6096. For the reaction, and for the process stream, it is a liquid only stream. For the reaction, the reaction that we added is mentioned here. And after this, we can click on the run button to see if there are any errors in the simulation. So it's trying to calculate, and you can see the results are available without any error. So up to the reactor, we have successfully complete our simulation. Now we need to add a different separators. Let's look at the results. If you look at the result here, we are getting a lot of water, and this water need to be recycled. So the way we can do this is we need to separate the water from the rest of the components, and then we can recycle them. So we need to add 3 different separators. The first separator, we can call it evaporator 1. Second separator, we can call it evaporator 2. The third one, we can call it evaporator 3. Then we need to use the outlet of the reactor to the inlet of this separator, and the bottom of this separator will go to the inlet of the second separator. And just now we can call it any random number, so because we don't need to display this stream, so we can call it with any number. The second one bottom will go to the third one inlet, and we can call it 1, 2. You just need to hide this ID, hide it, right. Then we have the top product from the 3 separators. Obviously these are 3 different separators. They all are basically used to remove the water from the rest of the components. So all these top products we need to add in the mix them in the mixer, and then we can send them back to the feed, where we can add this one. We can send this one further to the reactor for further reaction. So what we can do, we can click on the mixer. We will call this mixer with any name, just because we don't need to show the name. Then this one we need to rotate horizontally, and for the top we need to add this one by one. First one we can add, we can call it E1. Second one we can click on the second stream and send it to the second. Then we have the third stream, that is 3, and the outlet of this mixer will go to the inlet of the first mixer. Let's call it, which is water dash, which is recycle of water recycle basically. These 3 streams IDs are not required, so we just hide them, right? And then if you look at here, these 3 separators, if you open the separators, we can see we have to provide 2 information, the temperature and pressure. To provide the temperature, we need to use a steam, and this way what we can do, we can add a steam stream. This one you can call steam, this, and then we need to provide the information for the steam. The steam is operating 200 degrees Celsius with 1 bar pressure, and the mass flow rate is 27 kg, and this is mass fraction of water. Right, this steam obviously we have 3 separators, so we need to split the stream into 3 different streams. I can name it here, then I will hide this ID. and let's enter this stream to the splitter. The outlet of this we can see this is the first one, which is steam 1. This is steam 2, and then we have steam 3. Similarly, we need to hide the IDs, which is not required. Okay. Then all these 3 streams need to be further heated, so we need to use heater block for each separator. Right. You can move this one slightly down. So this one is entering to that stream. That one is entering to the second heater, and this one to the third heater. Okay. All right. Okay, so the outlet of any of these are just heat out 1, and this one is heat out 2, this one is heat out 3. We will hide their IDs, so the simulation looks slightly organized. Okay. Right. Now we need to provide some information. We already provide information for the steam, but we need to provide information for the splitting of the steam. So in this simulation, we will use those values which can be modified, can be optimized depending on the result. Okay, we need to make sure our flash option is, the error of tolerance will be as minimum as possible. We need to go to each of the heater and provide the individual information for the heater. That will be similar, I think, for all these heaters. That is 25 degrees Celsius and 1 bar. Similarly, we have for other heaters, which is 25 degrees Celsius and 1 bar, and the last one, which is 25 degrees Celsius and 1 bar. Right, after we provide information for the heaters, we need to use the heating block. Heat stream or energy stream of this one is used to heat evaporator 1, which is called Q1. Second one is used to heat the second, is called Q2. Third one is used to heat the third one, is called Q3. Right, now we need to provide only the pressure information for the separators. So the first separator is operating at 14 bar. The second separator is operating at slightly lower pressure, and the third separator is operating at 4 bar, which is lower than before. And we will make sure the flash options information is as low as possible, the tolerance of flash column is as low as possible. Okay. Why this is shown up here? Okay. All right. Perfectly fine. All right. So we are missing something. I think we have provided all the information. Do we need to provide anything else? And the flush option needs to be right. Let's see what information, what else we need to provide. Inlet board. Okay, we have some problem here, I think. Reconnect destination. Right, we have one outlet from the separator with the connection. That one is called evaporation out. Okay, so everything is fine. Then we can click on the next option. Still we have some problem. Inlet port, we don't have inlet port. Okay, let's reconnect this. Hoop is now fine. So click run. It will take some time because we have a recycle stream in the system. So let's see if it converges. So as you can see, the simulation is converged successfully. If we can take a look at the results for the vapor outlet, we can see we have slight reduction in water content, but we have increased the production of ethylene glycol, and then we have slight formation of triethylene glycol and tetraethylene glycol. Right, so we can further improve this process. Now we have ethylene glycol in our system, so we can separate all these glycols by using a separator which is called not a separator, which is called the red flag. We can start using the red flag. The first one is dehydration unit. Dehydration, you can call column, and this one is taking the feed inlet, and they have the exit streams as a distillate, which is a H2O that is purging, and then we have the bottom stream, which we can say N-AG. The absorber before I can add, I just want to save the simulation so I will not lose it and if I face any problem. This one is called glycol simulation. Alright. So now we need to provide the information for the column. The column is operating at equilibrium with 9 stages. It is the condenser is total condenser, is the catalytic type. Valid phase is a vapor liquid. We have reboiler duty and also the reflux ratio. This will be more and not 2 or the reboiler duty in megawatt, that is 25 megawatt. The stream information, the feed is entering at stage number 5. The rest of the information is as it is. Pressure, in this case we have a pressure profile, and that will be stage number 1. The pressure is 0.5 bar. We have no information for the condenser, no information for the core, for the reboiler. Right. After this, we can just run the simulation, and you can see immediately it is converges. What I can see on the top frame, if you can just show the result. Mole fraction, we see 99% of water on the top, which is what we require to do. Okay, so this is my water. Let me try to change the colors of the streams. That is important to us. For example, the first one is recycle stream, and it should be in red color. Then we have the steam in red color, and all the steam streams changing to a red color, and all those streams which is playing a role in the recycled stream, the color is to be red. Okay, right. Now after we add a dehydration unit, we need to remove ethylene glycol, ethylene glycols, and tetraethylene glycols. The way we can do this is exactly the same as we will do it with the dehydration unit. We will call this one MEG column because it is used to separate MEG. And if you we need to add this, and then we have one stream which is leaving at the top, and then we can call this MEG, and the stream which is leaving from the bottom is the rest of the components, which are N-EG plus. And if you can go into the MEG column, there are 26 stages. It is also a total condenser, which is the reboiler is kettle, vapor liquid phases, and similarly we have the reboiler duty and the reflux ratio that is 0.3, and for the duty in megawatt we have 23. The feed is entering at stage number 16 with the pressure profile pressure at stage number 1 is not 125. After that, we click on the run button and it will immediately calculate the information for us. If we click on the top stream results, we can see we have about 98% of ethylene glycol. So we have completed this part. Now we can click on, we are trying to remove diethylene glycol, which is also similar to the one which we did before. This one we can call DEG column. And the stream is entering, and it will give us one product on the top. That product is called DEG, and one on the bottom, it is called TEG plus. Right, we will go inside to the column, and we have the total number of stages are 16. Condenser total, the rest of the information is same. Again, it is the boiler duty and the reflux ratio, 0.7, and for Kelvin, this one is in megawatt, 202. The stream is entering at a pressure at a stage of 9, and the pressure profile we have is at stage number 1 we have not 0.1. After provide, we can click the run button, and it will give us some error. The following unit pressure block populated with errors. Okay, what kind of errors we are getting? Okay, at limit of some of them was imposed on the fluid. Okay. Alright, what we are getting is this number, the furnace which dried up. Okay, let's try with different configuration. Oh, okay, so I found some issue here. Before, the power that we use is about 2.2 megawatt, so we will reduce this to 0.5 megawatt, and if you can see now, it is converges. And if you look at the result of DEG, we are getting about 99% of DEG on the top. Right, so after we done the last one we need to do is ethylene glycol separation, and then we do the same exactly, and this one we can call TG column. The feed is entering the middle. We have one product on the top that is called DEG core, and on the bottom stream which is called OEG. Yes. Right, after this we need to provide the information for the column itself. The column is operating at 12 stages. It is a total condenser, and also the flux ratio 0.8, 0.1, megawatt. The stream is entering at a stage of 12. Above stage, the pressure profile in this case for stage number 1 is 401 bar. I click run button and it converges successfully. Now we can have a look at the streams results. The top stream should contain 99%, not the top stream, the bottom stream should contain, and the rest of the company, let me check that one. Right, you can see we have small quantity here. We are getting a very small amount on the bottom. What about here? We are getting a very small amount of ethylene glycol, which obviously depends on how much we are producing in the first place. So in this way we can able to remove all three glycols. Right, we can go here and change the power requirement and see if we are able to improve the results. It's not improved yet. Right. Alright, we are here, how much we are getting. Yeah, it gave us good. Right. Somehow we are not able to improve the results for TEG. Right. Anyways, we can see here we are able to remove ethylene glycol and diethylene glycol from our system. Okay. We want to see the temperature, pressure, mass flow rate. This is the simulation so far. We can do one case study, optimization study. In this simulation, we can click on model analysis, click on optimization, click on the ID, and here we need to, this one is mass fraction. It is a stream variable, and it is for and this one can leave it to all, and this one is mass fraction. Cycle mixed, and this one is EG. Right. Second variable we have is mass composition. That one is again, I'll leave it to all. That is a mass flow rate, mass flow, again for the recycle stream, to the mix, and it is for ethylene glycol. The objective function in this case is minimizing the mass combo, which is that one, right? And what we are trying to vary, add a new one. This is a block variable. It is for the split. Let me see what is the name. Give it to the split. That is B8. Okay, let me call it split. And then height. This is for split, and it is a flow to friction, that is for stage number 1. Lower bound is 1.1 and upper bound is 0.5. Similarly for okay, that one is for the second one. That is again a block variable. It is again for a split, and it is a flow to and it is for step number 2, starting from 0.1 to 0.5. Okay, after that we can click on the run button to see